Today we're going to talk about neutralization reactions. A neutralization reaction is when an acid and base are mixed together in proportions such that the hydrogen ions from your acid are neutralized by the hydroxide ions from your base. We're going to start with a very standard neutralization reaction between hydrochloric acid and sodium hydroxide. When these two substances are put into water, they're going to dissociate. Those dissociation products include the OH, or hydroxide ion from the base, and the H+, or hydrogen ion from the acid. When you put an H+ and an OH- together, you get water. So our first product in these reactions is going to be water. The next product in these reactions is going to be a salt. When we say a salt, it might be NaCl, or it might be something different. Our salt is going to be comprised of the leftover ions. In making water, we used up hydrogen and we used up hydroxide. This leaves behind Na+ ions and Cl- ions. And I know that Na is +1 and Cl is -1 from using the periodic table. So these Nas and Cls are going to form our remaining salt, which is NaCl. Remember, you do have to check this +1 charge and -1 charge here and bring them down to make sure you truly have your formula balanced out. Also, you always have to be sure that you write your positive ion first. Most neutralization reactions are going to follow a general formula we're going to talk about. Some of them are a little more complicated than others. The general steps we're going to follow are listed up front. If you need to, you may pause the video to write these into your notes. Step 1, we write the formula for the acid and the formula for the base as your reactants. These can go in either order, but they both have to be on the left side of your reaction. You need to make it, occasionally these will be given to you, so you don't always need to worry about step 1. Next, you need to write the formula for water and cross off the ions that have been used to make that water, which are typically H+ and OH-. You're going to write the formula for your remaining salt, and in that formula you need to make sure that you crisscross and, of course, write the positive ion first. Finally, you balance the equation just like we used to earlier in the year. If you need to pause for a moment in order to write these steps down, this would be a great time to do that. It gets a little trickier when you get into what are called diprotic acids. You can also have a base with more than one hydroxy group. It all just depends on how crisscross works out. So in this case up here, we have what's called a diprotic acid. It has 2 H+ in it. So you can see that little H2SO4 in the formula. And visually, you can see this in the graphic up on the board. So when H2SO4 and KOH are put into water, the H2SO4 actually gives us 2 H+ ions. Now we're going to talk about where that comes into play later. But we still know that the first thing we're going to make is going to be an H2O. And that H2O is going to be made up of H+ and OH-. So we have used those up in making that water. This other H+ right here is going to be turned into water. And you're going to see where this comes into play later. For right now, cross it out and understand that it's not going to be part of our remaining salt. And we'll show why when we balance. So what I have left to make my salt out of is my K+. And again, that +1 charge I know from looking at the periodic table. And I have the sulfate ion. And if you go to table E, you'll see that this has a -2 charge. I'm going to crisscross these. I'm bringing down my 1, and I'm bringing down my 2, giving me the formula K2SO4. So when we go to balance this, because really at this point we actually still have an excess H+ up here, and as you can see we have a 2 by the K that isn't really accounted for on the other side. So I'm going to set up a straight up balancing table, H, S, O, and K. On my left hand side I have 2 hydrogens right here, plus 1 hydrogen right here, giving me a total of 3. I have 1 sulfur, and I have 4 plus 1 gives me 5 oxygens, and I have 1 potassium. On the other side, I have 2 hydrogens here, 1 sulfur here, 4 5 oxygens and 2 potassiums. Now, general balancing rules tell us that we should not start with something that's in multiple terms on the same side, which is why I am absolutely not going to start with hydrogen. That would be a disaster. Oxygen, same thing. So I don't want to start with either of those. Usually it's best to find something in your salt that isn't balanced and balance that first. K2 here in my salt is not balanced out on this other side. So I'm going to put a 2 in front of KOH. When I put a 2 in front of KOH, turns that into a 2. When I count up my oxygens, I have 4, 5, 6, 2, 3 for my hydrogens, or sorry, 2, 3, 4 for my hydrogens. So I put that 2 out front. I did not change my sulfurs here. So now looking back at what I've got, I fixed my K, my oxygen, and my hydrogen are a little off. So when I look back over on my reactant or on my product side, there is a place where I can fix just oxygen and hydrogen. And I can do so by putting a 2 right in front of water. Now that turns this into 4 hydrogens here, 2 oxygens plus 4 here gives me 6 oxygens. My hydrogens are balanced, my sulfurs, oxygens, and my potassiums. Now to go back up here and talk about the situation that we had with that excess H, because I put a 2 in front of potassium hydroxide, that really means what I did here was added a second one of these guys. This OH right here and this H plus right here are now able to cancel each other out. This guy and this guy make one water. This guy and this guy make my second water, which is why I have a 2 in that reaction. So my final product, H2SO4 plus 2KOH, makes 2 H2Os plus K2SO4. Sorry. So we got to try a few of these out. Let's look first at the neutralization of nitric acid and sodium hydroxide. Doesn't matter which 2 you write these in, as long as you keep them on the left-hand side. So if you put NaOH first, that's cool. So HNO2 plus NaOH, so I've done my step 1. Step 2, I'm going to write water. That used up my OH and my H+. What I have left behind now is my sodium from right here, which has a +1 charge from the periodic table, and my nitrite ion, which is NO2 and has a -1 charge. When I crisscross these, those ones go away and leave me with NaNO2. If I go ahead and try to balance this, HNO, Na, I have 1, 2 H's on the left side, 1 N, 2, 3 O's, and 1 Na. On the other side, I have 2 H's, an N, 3 O's, and 1 Na. I'm balanced and good to go. Another example where I'm going to end up having a subscript that's going to cause me to need to do a little bit of balancing my reaction is when I react HCl with calcium hydroxide. Now I'm going to first go ahead and write my water. This water will be made up, oops, I'm sorry, I have 2 there. This water will be made up of OHs and H's. My remaining product is going to be comprised of calcium, which has a +2 charge, and chlorine, which has a -1 charge. This will give me CaCl2. When I go ahead and jump back to balance this guy, I've got H, Cl, Ca, and O. 1, 2, 3 H's. Remember to account for that 2 being delivered to that H. I've got 1 Cl, 1 calcium, and this 2 also goes to this O, so I have 2 O's. On the other side, I have 2 H's, 2 Cl's, 1 Ca, and 1 O. So the biggest problem I'm having so far is with my H's, my Cl's, and my O's. Keep in mind, H is in multiple terms, so it is not someone I want to start with. Typically, I like to look at someone from my salt to start with. Since I'm fine on my calciums, they're balanced at 1 to 1, I'm going to start with chlorine. In order to get 2 chlorines over here, I can go ahead and put a 2 in front of HCl. That's going to now turn my H into 2 from here, 2 from here, 4, 4, and it turns my Cl into 2. Now I'm still not balanced for oxygen and hydrogen. I need more oxygens over here, and I need more hydrogens. I'm sorry, I need more hydrogens over here, more oxygens over here. Easily fixed by putting a 2 in front of water. That'll turn hydrogen to 4, that'll turn oxygen to 2, and it didn't affect calcium or chlorine. 4 and 4, 2 and 2, 1 and 1, 2 and 2. These guys are all balanced. Because I have a little 2 with my base right here, it took twice as much acid to neutralize that out. These are the typical types of reactions that you'll be doing. I did want to show you one other example. This is on page 18, it's number 10. In this particular example, there's sort of a weird looking acid. It's a 2 group acid. That acid actually has a structure that looks like this. Oops. Structure, sorry. This H is able to leave as an H plus because of these 2 oxygens right here. They kind of suck on all the electrons and allow that guy to get dissociated. So when we write the neutralization for this, this OH and this H plus are going to form our water as expected. Our remaining salt is actually something called sodium acetate. If you look at your remaining ion, CH3COO negative, that's actually a table E ion. So you can write this as Na, CH3COO. Some people also write this as CH3COO minus with a little Na plus next to it. I don't love that because I think it's a little bit confusing putting your negative second. If we look to see if everything is balanced here, we have 2 carbons on our product side, 2 carbons on our reactant side. We have 3, 4, 5 hydrogens, 3, 4, 5 hydrogens on our product side. 1, 2, 3 O's, 1, 2, 3 O's. We are all balanced up. This is beyond what I'm going to ask you to do on your quiz, but I wanted to make sure that you saw what this reaction looked like.